Good morning. Good morning. Oh, good. I thought you all had a little more energy than me. Eh? Can you hear me? Yes. Without mic? Right. First of all, let me pay my respect to my teacher, Professor K.P. Abraham, in whose memory this hall is built. Professor K.P. Abraham is a renowned teacher. Probably Professor K.P. Abraham, Professor K. Vasu, Professor Anandaraman, and Professor Brahmprakash in the atomic. They are the persons who laid foundation of the metallurgy in the country. Maybe many of you would not have known about them. Probably you can Google them if the Google is there or not. One of the great teacher, without whose teaching our fundamentals would not have been strong. I'm an old man. Even now I remember the subjects taught by Abraham and K. Vasu. It has been absolutely useful in my career all through. Second, I don't have enough words to appreciate as well as the knowledge given by this Department of Materials. This is one of the Department of Metallurgy. Now the modern guys like Professor Abik has changed to Department of Materials Engineering. Okay, this is the Department of Metallurgy. They have taught not only the metallurgy, but how to face the world, how to utilize the subject in the career forward. This is the wonderful institution. I don't know how many of you know about the ranking of the various institutions. You may see sometime the ranking in IIT Madras is the top rank in India and globally. The fact remains, Department of Materials Engineering is many steps ahead of that. If you look at the subject matter, this is one of the very great recognized materials department in the world. Why I am telling all this is it is a great opportunity you are able to come to a seat of learning, and that too of an outstanding nature. And there you are here, and thank the ASM to make a bridge between the engineers, industries, and academia. The topic of today's subject is given to me by the Bangalore chapter, Metallurgy for Engineers. How many of you here are students, and anybody from the student community here? Good. Good to see a few guys. Nice. And how many of them from the industry? Great. That is wonderful. You know, the point is, most of them are from the SME. For the appreciation of the professor, the SME is a very different platform basically. The so-called promoter will be knowledgeable as far as his product goes. and he knows how to make this product and how to sell this product. But how many SMEs take the legacy through? Because as the years pass, the technology changes, requirement changes, scenario changes. Whether how many of them are getting proper orientation or tuition in the respective subject, connecting the engineering as well as science to the practicals. So this role of ASM is that, am I right? See particularly I would recommend the guys coming from there. And another thing is, average SME engineers, while getting the knowledge, will jump out to the larger industry. So they are the real base, like another academic institution, to give the knowledgeable engineers to the larger industry. So they have a great role in building the nation, right? So I warmly welcome you. And first, let me wish you all a very bright future. And I may not be there, but you all should become a wonderful professional in your respective organization, contributing to the growth of the country. Now I'll come to the subject, okay? Sorry, I had taken more time on that. Maybe I may exceed the time. You may have to do that. Okay. Now, the topic of it is the next one. The metallurgy for engineers. Who is the engineer? The guy who supports in manufacturing certain products. This is what your engineering college supports you, basically, right? So the many time I see the students coming out from the college, they feel, oh, something all we are taught, industry we are doing something else. I don't know how far it is relevant. No. As you go through your ladder, someday or other some problem will come. There, unless and until you are strong in science and fundamentals, you will not be able to think and give a solution. So you will be one of the onlooker in your industry rather than a contributor to the growth. So all this sort of a workshop or seminar or symposium, whatever it may be, it does the only to the extent of inspiring you to open the books and feel the seriousness of the every subject. I don't know whether the professor agrees with me or not. Okay. Now, why I say that give the periodic table, these are all the materials available, right? We were taught in the college or the PUC level, all the left sides are metals, right side are non-metals. Okay, next one. How does it matter to you? In engineering thing, various materials has to be used, right? The materials does not have any value if it is not used. You are sitting in the chair because it built up the materials. So how do you select the material? First, stability of the material in the given condition. You are sitting in the chair. It may have to carry a person of weight of 25 kg to 1.25 quintal or 1.45 quintal, right? Whether it is stability in the given condition. 2, ability to withstand the mechanical forces from various sides. 3, suitability of the performance at the given temperature. Why I say specifically this? Okay, in your factory you may say, yes, this is the material I selected, so and so. You know, many guys, when they go abroad, they have a fancy of bringing many equipments or the household active products to the country. Even now, our white man's craze has not gone out fully. Even though the government of India is trying to talk about quite a lot about the patriotism. So many of you go abroad, your house people or wife or girlfriend will say, bring me that, bring me that. What happened? That are all in the cold places, temperature is very low. When it comes to India, it will not work. You have to show a bad face. So suitability of the performance at the given temperature, that is the most important. Meeting the conductivity requirement, electrical or thermal. Equally important is the corrosion resistance. Why I say is recently somebody bought a valve. Well plated, looks like a stainless steel. He gave it one of the equipment also bought. When he started, the valve failed. Basically because the plated one inside the material is not the right one. So the corrosion is a very important. Whether it needs a bearing quality or not, given that. Wear resistance is there. And above all, it's cost compliance. Whatever I am going to talk in next 20 minutes, everything you will find in Google. So my interest I am not going into the depth of the technical portion of the metallurgy, because the time is, then you need at least one day for me. Within 20 minutes, whatever this thing is there, then you can go into the Google, research it, you will get all the information. So if I have inspired you to get into the Google, at least see the 2 words or 2 sentences, I had done my job. If you are not, then I have made you to sleep only, right? Okay, that is why this thing. Okay, next one. When you talk about the engineering materials, you have got both metallic, non-metallic, composites. In the metallic, you have metals and alloys and metalloids. Non-metallic, you have got the polymers and the elastomers. In the composite, typical example is fiberglass, ceramic matrix, metal matrix, and concrete. This is a very classic example of the composite. You don't need to go anywhere else to see what is the composite is. Next one. Next. See, why this all you will know, understand, every material what we use is taken from the Mother Earth. Everything is available here. So what the percentage what I have given you is taken from some book or something like that. It may be accurate, it may not be accurate, but it represents the by and large source, right? These are all the materials, metallic materials available in this thing. Next. Why I given this? I will take back to you your school time. Maybe 8th standard or 9th standard. Why I specifically do is, do you remember what was taught in the 8th standard, 9th standard? That is what I want to inspire you, right? In the 9th standard, you find definition of the metal. Any metal which is put in the dilute acid should have all hydrogen. That is the definition of metal. Probably the modern time the definition of metal would have changed quite a lot, but this is the one what is taught in the school. And what is the aspect of the property of the metal? Malleable, ductile, electric conductivity, thermal conductivity. Now you have got an electronic property, etc., etc., etc. These are all the basic things what we were taught in the schools. How many of you remember this? Everybody is sleeping. One fellow is yawning, another fellow is sleeping, right? That is the outcome now. Right. Next. Now when you talk about the metallurgy, you have got a process metallurgy. Process metallurgy is mostly the chemical area. Physical metallurgy, electrometallurgy. In the process metallurgy, you have been taught about thermodynamics, which many students find boring even now, who are all weak in mathematics, chemical kinetics, and metallic structure. That is what the structure of the material is what is taught now in all the materials institutions like IITs, IISc, etc. It is a structure. And the electrometallurgy, electroforming, you can stop me at any given time and ask any question, okay? You don't need to wait till the end if you really want anything. Next. Moment you talk about structure of the metallurgy, metallic materials, basically you have the body-centered BCC, FCC, and hexagonal, and something more also, but this is the most popular one. Why I brought this for the next one? This is what it looks like when you talk about the metallic structure, which is neatly organized. It is what it looks like, the metallic. Next one. See, this is what I want to do. Because most of your industry guys will be dealing with the iron-based material. Particularly, you have some lectures about the heat treatment today, isn't it? Right? So, most of the heat treaters will say quenching it, hardening it, tempering it, etc. These are all the words they use. They don't use the word of any, why it is happening, not many of them talk. Okay. And everybody thinks in the mechanical thing, when you heat about so and so temperature and quench it, it will become hard. No, that is not for all the materials. So typically, you have a normal iron is a ferrite and the austenite. I'll come to the ferrite and austenite separately when you come heat treatment. When you have a heat treatment lecture, you ask him at the time. I'll give a small dose on that. Next one. When you talk about, again the heat treaters will talk, when you talk about the heat treatment, they all based on the ferrous heat treatment, basically based on the iron carbon diagram. Anybody going out of the engineering college, mechanical engineering also, will talk about the iron carbon diagram, particularly useful for the understanding how which phases contributes to which one of that. You go back to the previous slide. When you come to the iron carbon diagram, you hear so many words like this: perlite, cementite, martensite, bainite, etc., austenite. These are all the normal terminology heat treatment people will. Why I am asking specifically, the guy who gives a lecture today in the heat treatment, if you want, you can weave this to that his heat treatment process. For your information, the austenite is a phase when you quench, it retains the high temperature thing, it doesn't get hardened. Okay, so the normal ferrous what you have is a ferrite and bainite, that is what it's getting hardened. Another one is formation of martensite. If you want what is this each one has got a crystal structure, later you ask me, I will tell you. Next one, right. How much of time I have? Go ahead. I'll keep my mobile here so that then how all this heat treatment, how do you decide? Based on the phase diagram. What is a phase diagram? You make an alloy. What is an alloy? Two or three different metals dissolve in each other in the liquid stage. Then only it forms an alloy. So, I'm typically showing some thing. So, for example, if you look at it, it is the copper nickel, this thing. Whatever you see here is the liquid area. Whatever you see here is solid area. So, you talk about liquids and solids. I don't know how many of you remember, doesn't matter. So, when you look at the solidified, this is the phase structure. You will have liquid, it will mix uniformly or non-uniformly also. Okay. Next one. And the earlier phase diagram only I talked about the iron carbon diagram. Okay, that talks about so the phase diagram decides what microstructure you will have at the room temperature and what type of a structure you would like to have depend upon how fast you cool it, how fast you heat it, etc., etc. So I talked to you about the iron-carbon phase diagram, and totally mixable two alloys is a copper-nickel I showed. This is again another popular one, aluminum alloy, aluminum silicon alloy. And this is known as eutectic. Okay, that is the lowest melting point. Say. What happened when you quench this alloy? From here you bring down the temperature, it will have that phase as well as this phase. So this is, see there, now in the Google you can get the phase diagram of any materials what you have. So whether these two materials will form an alloy, open the phase diagram whether available or not. That's all what is required. You got my point. I'll tell you one more example. In the aluminum foundry, when you go, they degas it. What for they degas? They remove the hydrogen, because hydrogen is soluble in the liquid aluminum, insoluble in the solid aluminum. So it forms the bubble. So what they do? They degas it with the nitrogen or chlorine. It forms a bubble and the hydrogen ions comes in the bubble and come. Why nitrogen? Nitrogen does not dissolve in the liquid condition as well as solid condition, so it is used as a purging agent. So this sort of a common sense you should have. You understand? See, this is why I am telling you, this is all the basis. I don't know whether anybody talking about the foundry today. If it is there, you ask that question. So this is if you go to the foundry, somebody using so and so, this is the purpose is that. And many times they use the argon, but argon is very expensive. They use the nitrogen or chlorine, whatever it may be. Go to the next one, right? And this is the microstructure of various things. When I talk about this aluminum, silicon, magnesium specifically, when you go back to that, there, like a steel, aluminum also heat treated. So you get into the two normal terminology is quenching and age hardening many times. What is age hardening? When you, this sort of a thing, you add some magnesium silicon forms a small precipitate. As the temperature, it grows into the microstructure and becomes, it stresses, so it becomes age hardening. So this is all basically because of the movements of the atoms or the precipitates which various take. When somebody talks about heat treatment, talk to them about what is martensite, why it's happening like that. Okay, if you quench the aluminum, nothing is going to happen. It's not going to become hard or anything like that. It is only high temperature structure it's going to maintain. Okay, next, go to the next one. These are all the different types of the microstructure. What of as I told you earlier, in the iron you talk about the ferrite, austenite, etc. That structure is like this. There is a Professor Abik is a fund of knowledge, internationally recognized great man about the microstructure. And for him, you tell various elements and the composition, he will tell you what microstructure is going to be. He got a model, a very great man. Later, when you want to have interact, you can come to him, provided he has got a time. Am I right, Avik? next, okay. See, for you to read what looks like ferrite, what looks like a martensite, what looks like in the microstructure. You talk about nearly about 800x magnification, right? You see all this. What is retained austenite, etc. Go to the next one. Typically, aluminum silicon microstructure, what I told, magnesium silicon system precipitation. Next one. In the modern time, in the iron, you have got, very often you hear duplex steel. See, normally you hear about what? MS and mild steel and various low alloying steel, EN8, EN24, etc., etc. You have some ASTM specification. Then you come to stainless steel. Stainless steel, as a definition, it doesn't form a stain, it doesn't get corroded. There, again, stainless steel you have austenitic stainless steel, like 316 and 304, martensitic stainless steel, So for you to understand simply, any 300 series, this thing, austenitic stainless steel. So when your boss says 300, when he takes the 400 series stainless steel, you say no. The 300 series is austenitic stainless steel which can't be heat treated. 400 series is the martensitic stainless steel, can be heat treated and get into the various hardness. And the third variety is available, duplex steel. You have ferrite and austenite mixed together. It is a highly corrosion resistant. When you talk about corrosion, I'll tell you there's one a per number, just remind me, I'll explain to you at the time. Highly corrosion resistant, high strength, etc., is a cost compliance. So this is structure is what it's going to. Why I say is, when somebody gives you stainless steel and gives a microstructure, you should know, it is only austenitic steel or non-austenitic steel, it is not a duplex steel. You should be able to know. Now a lot of laboratories are there, you go there, here they give microstructure, right? Go ahead. And some laboratories really qualify, somebody may not qualify, because the qualified man would have gone outside in the day. Next one. See, now you have got modern materials like titanium, which you would not have heard about 25 years back. See the structure of that, various. So, microstructure should somebody who is interested in microstructure should thrill you, seeing the various patterns, etc., and you should be able to provoke you what type of outcome you are going to get out of it, what type of properties you can expect out of it. Go ahead, next. Various types of microstructures for you to see that. Have a look at. Go ahead. Next. Okay. Now coming to the engineering operations, various what all the engineers basically do. Casting you have, welding you have, metal forming, heat treatment, machining processes, advanced manufacturing processes, forging, extrusion, additive manufacturing, electromachining, physical vapor deposition. I have been taught here by Radhabai here, okay. Those days it was only institution talk about the PVD, vapor deposition. One day after teaching, I remember TVS called me to give a lecture how to, in your dome, how to make a reflection without this thing. So you get the mirror, in the front side it's a polish, so that there is no loss of the depth. So when I talk in this department, I get my old memories. That's why I'm intervening in. Pardon me for, I may go out of the subject, doesn't matter. Additive, the PVD and injection molding of the metal. I will just take about 30-40 seconds in each one of that. Casting, as you know, you melt the material, maybe pure material or alloy, whatever the composition you want, and you have what they call a grain refiner and degassing, etc., whether it is copper, then pour it into the mold. Two things you keep in mind, 2 or 3 things. The defects in the casting normally come out of shrinkage, gas porosity, and inclusion, maybe slag or other inclusion. What is shrinkage? There is a volumetric change between the liquid metal and solid metal. With the exception one material, I'll just come to that. So that is shrinkage. I'm not getting into depth, but I want you to know. Blowholes mostly out of the gas porosity. Third one is the inclusions like slag inclusions or the other impurities inclusions. These are all the things. So, and the metal, when you design a mold, you should have the shrinkage allowance for 2 things. Solid to liquid shrinkage allowance, which is compensated by the risers, and solid to solid shrinkage allowance is compensated by the pattern maker. Okay, so when you go to the pattern maker allowance, what is pattern maker allowance? You should understand that. Any subject in foundry today? No. Yeah. So, right, he will cover it. I'm just giving you should ask more questions to him, right? Welding, you know that. You melt the material and fuse 2 things, maybe by the gas welding, electric arc welding. In the electric arc welding, you have got a TIG welding, MIG welding, etc., various things. Fuse the material. When you talk about the welding, which you very clearly should understand, heat affected zone. where the properties will be different from the expected one. So you look into that. Metal forming, you may be rolling, wire drawing, extrusion. These are all the metal forming areas you have. Heat treatment, I talked already about that. There is what lecture on the heat treatment, isn't it? He will. Three lectures. Please hear that, because most of you are the heat treatment background. But get into the fundamentals, right? The heat treaters normally, pardon me, fundamentals they may not go in, right? Please get into that, so that it will stay in your mind and your mind will work. Various heat treatment you also can bring out. Machining process. Those days we were talked about only about the lathe and the milling machine. Now variety of machining process has come, and your CNC machines have replaced the human skill. Absolutely, you can talk in terms of micron control and various shapes, 2 axis, 3 axis, 4 axis, 5 axis, any axis will come, right? Advanced manufacturing processes, many this thing comes. Forging, heat the material and make it the shape. You can see on the roadside those days, now you don't see that, right? And
what are the advanced manufacturing processes?
I'll come to that. At the end, I'll come to that. I would have covered by that, that's why I just kept it, okay? And forging, you know. Extrusion, you have heard about it. Additive manufacturing, that is the order of the day. You take the powder, program it, layer by layer by layer, you build it. So various shapes, which you can't get it out, say, in the casting area, I think, and variety of when you want to reduce the material. See, when somebody gives a lecture, they talk all about the using the powder in the vacuum area, laser welding or electron beam welding, etc., something like that. You ask them one more question. You got a laser cutting machine. That itself can be used as the additive manufacturer. You ask him that question at the time. Okay, I'll come to that. You ask him. So what I'm telling is, you tell your boss, don't waste your money for the bigger one, I will use this. He will be surprised. That's why I'm telling you, right? And the electromachining. The simplest electromachining what you have seen is your EDM, wire cutting, gear cutting, etc. Apart from that, you have electrochemistry used with the electromachining properly, what is the shape and what the various difficult alloys in the particular shape using a former. This comes to one of the advanced manufacturing processes, right? Physical vapor deposition. It is PVD, what they call, or sputtering. In the vacuum chamber, you sputter. You create the ionic this thing, and it goes and deposits in the target area. Very thin films are formed, maybe in terms of a few microns, and absolutely new technology. We were taught about 50 years back. Now it has come very popular, right? And what I'm telling is, see the institute greatness. 50 years back they had taught me. We had done the experiments also. Powder metallurgy, you take various pure metal alloy, mix it, compact it, put it in the furnace, sinter it and take it out. Powder metallurgy. Injection molding, you mix the powder with a certain binder. Inject in like a plastic injection molding, injection molded, put it in the furnace, sinter it, you get a good material. Very good, nice shape, various. This is again one of the advanced manufacturing processes, right? So these are all some of these things, the terminology you would not have heard earlier. Now you can hear. Is somebody talking about additive manufacturing today? You ask many questions. A brilliant expert from IIT Tirupati is there. Ask him many questions, right? Okay. Go ahead, next. Now the engineering operations, as already I talked to you about it, sand casting, permanent mold casting, investment casting, skews casting. Skews casting, I don't know how many of you heard. If you have not heard, if you want some doubt about it, ask me later after during the tea time or coffee time. And so what is that you expect? You expect a defect-free casting. So this is in the order of that. Centrifugal casting, how is use a centrifugal force to splash the liquid metal one layer after another, so that the cooling time is very fast, good microstructure, and with a very little defect what you have in that. A variety of welding process I have given there. Forging also at the other area, metal forming area given. Next. But just keep on looking at me. Engineering operations, you can go through that. Surface hardening, solutionizing precipitation. Solutionizing precipitation only in the aluminum and some of the copper alloys comes. Steel, it may not come. All that. Quenching, annealing, edge hardening, I explained to you. Milling machines and the powder metallurgy, additive manufacturing, I talked. See, there is one more thing I missed it until. Spray forming also is there. Somebody is talking about metal spray, isn't it? You ask them those questions. Thermal spray, you roll new technology. Understand that. Next. The normal metallic materials, whenever you talk, these are all the values you talk about. What is ultimate tensile strength? What is the elongation, whether it suits me or not? What is the hardness where I require? Whether it gives enough abrasion resistance or wear resistance? Fatigue. How many of you know the terminology fatigue? One. Then two. Good. Fatigue is a very important terminology. You know, when you run, initially you'll run very fast. Then you become tired. That is known as fatigue. It is a metal fatigue. It's a tiresomeness of the metal, particularly in terms of the alternate stress and strain, the fatigue will be aggravated. Somebody talking about fatigue today? But you are talking? I see. So, especially the rotary shaft designing, etc., the fatigue factor should be taken into account both by mechanical designs as well as endurance tests. Right? Fatigue. Creep. How many of you know? Creep. Good. It's a time-dependent deformation. The day when you put it, you will not see. This you see very often. Many people in the house, they put the drying of the clothes, a thin wire they put. After some time, it will keep on going. That is a creep, right? Typical example I'm telling you. Creep. Then electrical conductivity, thermal conductivity, etc. Pardon?
You missed the temperature.
Yeah, that's true. So these are all the normal engineering properties which you have to think about. Next. Typical stress strain diagram. I want you to have a look at it. And many materials, when they select for your thing, calculate the load. Whether it's suitable or not, you can go to the, now earlier we had to run for the books to give so and so, the stress strain diagram. Now everything is available in the Google. Please utilize that. For any one of the selection of the materials, utilize that, right? So you, by and large, you all know, but read it. Next. See, this is I talked to you about the fatigue. This is an interesting curve. I want you to only remember the name, SN curve. If your operations is below this, fatigue failure will not be there. If it is above this, fatigue failure will be there. Then you go to the internet and read all that. See, normal mechanical engineers coming out of the college, what I am saying is, about 100 guys, when I interview, SN curve. Gottilla. That is the answer. So please refer to that. Very important curve, easily available now for you to know whether you are safe with the fatigue failure or not. Okay. Fatigue number of cycles, alternative stress and cycle. This is next one. Afternoon heat treatment, who talks about it? Especially for the iron, whether he talks about TTT curve, whether the quenching is a, see this area, when you come to quenching this area, you go through the phases, you go through that, ask him the question and read the books. Correct? Next. See, now you have not only for the human being and animals, metals also got a memory. That is why what you got shape memory alloys. You can design a metal in a particular combination. In so and so temperature it will have this shape, so and so temperature it will have this shape. Many of the aerospace items, slightly temperature is higher, it just bites it very well. At the lower temperature, you can just assemble it easily. So these are all the shape memory alloys. During those days, we never heard. Abhik, for our project, NAL Krishnan, when I started the foundry, he used to come and ask me about the copper thing, shape memory alloys. I never understood what, I made the alloy and gave it to him, but this is what it is basically, right? Now you have got the nickel titanium alloy, copper aluminum zinc alloy. This is all shape memory alloys. You can go through that. Next. You got another material, electronic material. What is inside your ICs? What is inside your SCR, diode, etc. In fact, I can give a 1 hour lecture on that, but I have not prepared. The time is not permitted. Understand that. I give a typical example of that. These are all the modern materials, right? Which normal, I don't know whether how many regular mechanical engineering classes they talk about it.
Not really.
Not really, isn't it? So at least you should hear the name, right? So that you are not left out. Next. Electronic materials, I have given the piezoelectric material, superconductor. Superconductors, very often you hear a very towering personality, C.N.R. Rao is here, he talk about superconducting in the Institute of Science, quite a lot about it. And he got his, Bharat Ratna and all those things for the superconductors, right? And which is used in your MRI. You all go to the hospital and lie down and somebody takes a picture of it. No, that use a superconductor. Go through the internet later. Go next. Nanomaterials. See, the way the nanomaterials, the material in the normal material, the microstructure or the powders are totally different behavior and properties when it is ground to the very fine area of the nano size, that is nanomaterial. Now, many of the nanomaterial area have a conductivity more than the gold. Am I right? I'll give you one typical example which normally the metallurgy professors would not like to talk. Mercury, you all heard, isn't it? In Kannada, it's known as Rasagundu or something like that you talk. Padarasa, correct, exactly right. See, the allopathic doctors and the mercury is poisonous, it will kill you, etc., etc. They terrorize you. When you go to the traditional Ayurvedic or Siddha Vaidya, they use solid mercury, Rasagundu, they use. What is the solid mercury they get? They keep on grinding, get into the nano level. And that has got a lot of medicinal properties and become solid. This is one of the, so don't tell me the nano was never talked about those days. All are available, some of them are available in the literature. So this is a typical example. Go into the details and get yourself be thinking we had done something in those days. Right, go ahead, further. Next. Types of failures when you have overloading, brittle failure, failure due to the fatigue, and the stress corrosion cracking. Again, if we want to talk to, you are talking about it, eh? You are not talking, are you? Okay, stress corrosion cracking. Right. No, next time let them come forward, but I want corrosion seminar one day, I'll give you, right? Okay. See, stress corrosion cracking. Many times the mechanical engineers will not know why it has failed. Especially during the corrosive agents or liquid time, stress corrosion cracking take place. Hydrogen embrittlement. Ship, the ship what you have, what material is the sea-going ships are made of? Any idea? How many can answer? The sea-going ship hull, what is the material made of? All are sleeping.
Iron, sir.
Huh?
Iron, sir.
Is it still?
Correct. It is a ordinary MS and protected by so many methods. There, in one of the protection methods, hydrogen evolution, the hydrogen can get into the microstructure and crack the material. Hydrogen embrittlement and failure due to corrosion, failure due to abrasion, and where. Why I'm introducing all this terminology? Because when you come across, you should be able to know. You understand? That is the reason. Next. I talked about corrosion basically because this is a subject which is very dear to me. Though this guy said, don't talk about it, I will take only 2 minutes, okay? Because this is a subject very dear to me, and many industries utilize this thing. Definition of corrosion is, it follows our Rigveda. All materials come from earth, but naturally would like to go back to earth, including human body. So that is the definition of the corrosion. It is defined as the degradation of the metallic material by chemical reaction with the environment. Corrosion can never be stopped, can only be stifled. Why I say specifically corrosion? When I asked the interview with the mechanical, what is that you know about corrosion? Rust. Bus. That is all, the matter ends there, right? So every metallic material undergoes corrosion. When exposed to certain environment, chemical reaction takes place, and you have to protect it. Go further. How do you stop corrosion? One, by selection of material. Gold, platinum. It will not get corroded normal. But you can't have everything in the gold and platinum. So how do you prevent the corrosion? One, isolate the surface from the corrosive environment. Like what? Painting, plating, some other treatment, covering it. What we do the dress, when we wear the dress, where our body is not getting corroded. Otherwise, chemical reaction. Say our shirt and pant is the corrosion protection area. Am I right? This is the one. Isolation from the environment. Then I have used the word cathodic protection. Whenever the water is available or liquid is available, the corrosion takes place wherever the corrosion takes place. It is known as anode. I'll tell you again, 8th standard or 9th standard, your teacher would have taught you one subject, voltaic cell. How many of you remember? Nobody? I thought only after going to college you see something else. But in the school also you get attracted to something else. In the 9th standard, you have what is known as voltaic cell, they show. One copper electrode and one zinc electrode keep there, nothing will happen. Connect it, zinc will get consumed, copper will protect it. So why the copper is, so long as zinc is there, copper is protected. That is cathodic protection. So any structure is getting corroded, convert into the cathode, it will not get corroded. That is known as cathodic protection. I don't want to get into details because the subject is very dear to me. And similarly, you have got anodic protection. Wherever sulfuric acid comes, you utilize that. Next one. Next. Thank you. Right? Anything else? You can ask me later. Thank you. So nice of you. Thank you for your patient hearing. I don't know, this last 25 minutes has been useful to you or boring to you? Pardon? Yeah, but so majority for it is boring. Only very minority is useful. Thank you for a patient hearing. Anything later, probably you have the panel discussion and I'll answer you. Thank you. So nice of you.
Can take 1 or 2%.
No, it will be, I'll be eating into others' time. Right. Thank you, so nice of you. So again, let me wish all the youngsters a very bright professional future, right?